This is the video on the fundamental theorem of algebra. It's on page 7 of your notes, 7.6. Here's what the fundamental theorem of algebra, it's a great theorem. It really is the nuts and bolts of what we've been talking about. It brings everything together. Here's what it says. It says that if you find zeros, you've actually just found a number of things. So there's a number of things that are all the same. What you've actually found is the x-intercepts of the graph. So we talked about that. You've also just found the solutions to the equation. You found the numbers that help us make factors. And if you happen to be working with a quadratic, you've also just found the numbers that come out of the quadratic formula. All these things are related. They're all the same thing. And I just think that's super interesting. If the zeros, these are the numbers that if you plug them in, you get 0. Now you know what the graph looks like. Now you also know the solutions to the equation. You can factor, and you can figure out what numbers come out from the quadratic formula. That means if you're ever stuck on a test or a quiz, if you can do even one of these pieces, you can do the whole thing. So if you can graph and find x-intercepts, you just found the zeros, which are the solutions, which help you factor, and you don't even need the quadratic formula. Or if you're really good at the quadratic formula, you get the numbers out, those are the solutions, you can make them into factors. Those are the zeros and the x. You get the idea that once you know one of these things, you know them all, and I think that's pretty cool. The problem that we're going to run into is that sometimes our zeros are going to be real numbers, just the numbers we use every day, but sometimes we're going to get imaginary numbers, and that's where things get a little bit tricky. So we need some other skills aside from just using our calculator or using the quadratic formula or whatever. So here's the question. How many complex zeros? That's a weird way to ask a question. Complex means it might be real, but it might be imaginary. So if I ask you to find, or ask you how many complex zeros are, what that means is, what's the total? The total of your real ones plus your imaginary. Well, the nice part about that, guys, is we can just look at the degree. We can look at the degree. Look at the biggest exponent, and that will tell you how many zeros you're going to have. Some of them real, some of them imaginary, and so on and so forth. The follow-up question to that is, all right, now that I know how many zeros I'm looking for, I want to know how many of them are real numbers and how many of them are imaginary numbers. So to answer that question, it says how many of the zeros are in the real family. Well, that's where your graph comes in. This will be the same as your number of x-intercepts. So graph it on your calculator, and it will tell you. How many of them will be in the imaginary family? Well, whatever ones are not real have to be imaginary. So if you take your degree and you subtract your number of x-intercepts, you'll get your number of imaginary zeros. Well, okay, what do you mean? Let's say I have a graph. I'll go right over here and draw a graph. And say the graph looks something like this. It goes down, up, and down. Like that. Just sample graph. And I tell you that the degree is 5, that this is y equals x power 5 minus 4x, or 4x, yada, yada, yada. It goes on and on and on and on, like that. So what you know, you see the degree here is a 5. That tells you that it's a 5th degree polynomial. When I see that, you say, oh, that means I have a total of 5 zeros, 5 complex zeros that I need to find. Well, I would look at this and say, all right, how many of them are real and how many of them are imaginary? Well, here's a real one. I can find it right on my calculator. Here's a real one, and here's a real one. So I see here that 3 are real, and that means that 2 are going to be imaginary. Because that's just 5 minus 3. So looking at your degree and looking at your x-intercepts can tell you how many you have of each. Now your non-real ones, your imaginary ones, are always going to come in pairs. They're always going to come in pairs. And not only are they going to come in pairs, they're going to come in complex conjugate pairs. If one of them is a plus bi, and the other one then the other one will be a minus bi. So they'll always come, like I said, not only in pairs, but they'll come in complex conjugate pairs. A question would why would it work that way? Well, we get our imaginary zeros, we get them from the quadratic formula, and it goes negative b plus and minus the square root all over 2a. So what's going to happen is you'll have a number, and you'll add it, subtract, the number goes there. So you'll add it, get a number, subtract it, get a number. So they're always going to come in complex conjugate pairs. The last little trick that we need to know is something that's called a multiplicity of zero. A multiplicity of zero is multiple zeros at the same x-intercept. Same x-intercept. Well, what do you mean by that? How is that possible? Well, let's say I have factors, because like I said, we know that all of these are related, zeros, x-intercepts, and all that. Let's say I have factors that look like this. So I have two factors. I have x minus 1 and x minus 1. Got the same one twice. Well, I know that factors and zeros are related, and if I look at this, here I have the 0 right here is going to be 1, and the 0 right, I have the same 0 that comes up 2 times. So, well, what is the graph going to look like? So I have the same 0 twice. If I FOILed this out, I would get x squared minus x minus 9 minus 2x plus 1, like that. So this would be the polynomial for that. And let's take a look at what it looks like. I'm going to very quickly graph it on my calculator. I'll clear this out. We have x squared minus 2x plus 1. Take a look at the graph. Here's what we have. You see that the number 1 is touched by the graph. And this is how we recognize multiplicity. If the graph comes down and just touches it, if it just nicks it, you might say if the vertex of the parabola is right on the x-axis, then we're going to have multiplicity. There'll be multiple zeros right there, so that's what that means. All right, here's a question for you. Let's see if we can do this. We're going to find the zeros of this polynomial right here. So we know that all of these are related. So we can use all the tools that we have available to us just to break it down. So I think hands down the easiest way is to graph it on your calculator. Or actually, no, let's factor. Let's try factor. I'm going to factor an x out of here. So if I factor out an x, I'm going to have x squared minus 6x plus 9, like so. When I do that now, let's try to break it down again. If I do this means I have an x in each, like that. Looks like this number is positive, so I know my signs are the same. I'm going to go minus and minus, put a 3 and a 3, like that. And if I'm finding the zeros, a 0 is here, a 3 is here, and a 3 is here, like so. So this is what I call multiplicity. Here I have a 0 of 0, and here my zeros are 3. The number 3 occurs twice, so I'm going to say I have my zeros, I have 0, and then I have 3 with multiplicity of 2. With multiplicity of 2, that means that it should, let me try that again, of 2, that means that it shows up 2 times. Hey, let's go ahead and take a look at that graph. I'm going to go x power 3 minus 6x squared plus 9x, like that. Graph it right here. You can see, look at that. It's going to go up. It's going to hit 0, exactly what I said. Comes up. How high? Don't know, don't care. But it's going to come down and just touch the number 3, and it just nicks there. The vertex, or that local minimum, is right on the x-axis because there's multiple zeros at that very same spot. All right. If we're looking at this, guys, it says, what's the lowest possible degree of the graph below? So, no graph below. Let's start at the bottom here, like that. What's the lowest possible degree? Well, if I'm looking at it, I would say, all right, here's a real, here's a real, here's a real, here's a real, here's a... So I know that I have 5 real. So I know that the degree of this is going to be at least a 5. Now, there might be some imaginary zeros in here that I don't really know about, but I can say I know for sure there's 5 real, so the lowest possible is going to be degree 5. So the degree equals 5 or more. All right, let's put this into practice. Let's try all the tools that we have here. says verify that 3i is a zero of this polynomial. Well, here's what we know about zeros, guys. That when we do division, if it's a factor, what should be the case is that the remainder, if it's a factor, then the remainder should be equal to 0. We're going to rely on our remainder theorem for this. Our remainder theorem says this. If you want to know, if I do division with this thing, and if I want to know what the remainder is, just plug it in. So what should happen is I should be able to plug it in. If I get 0, that means the remainder is 0, which means that it's a factor. So let's try it out. I'm going to go 2 times 3i power 3 minus 3i squared plus 18, still on paper here, times 3i, like that, minus 9, like so. I think I showed you in class yesterday, but just in case I didn't, your calculator actually has an I button right on it. So if you look down and look right here at your decimal point, if you hit second in the decimal point, you're going to get I. So I'm going to go to my calculator and let's just plug it in exactly how I wrote it on my paper. I should be able to go 2 and then go 3i like that, power 3 minus 3i squared plus 18 times 3i minus 9. So here's the moment of truth. If I punch it in and get 0, well, we got 0. That means that this is going to be a factor. So we know it's a factor. Now if it says find the remaining zeros, well, let's take the tools that we know and let's figure it out. Well, let's, I know how my calculator works. Let's graph it and find our zeros. So I'm going to go y equals, this should, when I look at the graph on my calculator, it should give me all the real zeros. So I'm going to go 2x power 3 minus x squared plus 18x minus 9. Like that. First I'm going to try graphing it on a 10 by 10, see if it works out all right. All right, well, hey, I have something to start with. I know that right here, what does the graph look like? It's not a very good graph. But I do know that right here I have a real 0. So let's take a second to figure out what that real 0 is. When I use that real 0, let's see, put a marker on the left, go over to the right, put a marker on the right. And, looks like 1/2 or 0.5 is going to be that real 0. So if I'm finding all the zeros, first of all, I look at the degree. I know that there's going to be a total of 3 of the numbers. So I have 1. In the part A, I found that 3i is one of my zeros. I just went on my calculator and found that 1/2 is one of my zeros. Now let's see, what else we can figure out. We got to find all the zeros. We're looking for a total of 3 numbers. So let's see if we can figure this out. Actually, one of our best tools that we can use, and you're going to love this, is polynomial long division. So here's how it's going to go. I'm going to take this polynomial and write it out. I'm going to have 2x cubed minus x squared plus 18x minus 9. And I'm going to divide out the 0 that I already know. So if that's 1/2, let's take a second. Let's turn this into a factor. It's going to be x minus 1/2, like that, which would times 2 and times 2 is actually 2x minus 1. That would be the factor that I know I'm going to use for this polynomial. So 2x minus 1 is what we're going to divide out. So here's the logic. Here's what I know. I know that 1/2 is a 0, so I know this is a factor. If it's a factor, when I do division, I should get a remainder of 0. So right away, already I know that if I do this division correctly, my remainder should be 0 when I work all this out. So let's try it. If I want to change a 2x into a 2x cubed, that's just going to be a regular x squared. So x squared goes right here. I'm going to go x squared times 2x should give me 2x cubed minus x squared, like that. And, we have something kind of weird. The whole thing cancels out. You get 0. We're going to add 18x, like so. We say, all right, 2x is going to go in here. It's going to be a 9. Remember that 9 goes over here in this column. So here we have 9 back here for 18x, like that, minus 9. Drop the 9 down, minus 9. When I subtract them, I'm going to get 0 for a remainder, just like that. Sorry if I was off the page a little bit. So when I subtract them, I'm going to get 0. So my answer up here is x squared plus 9. If I asked you to factor this, here's what we would say. We'd say one factor is 2x minus 1. The other one is x squared plus 9. If I asked you to find zeros, what we could do is we could take each piece of this and set it equal to 0. So if I took 2x minus 1 and set that equal to 0, and 2x minus 1, set that equal to 0, I would add 1, and we get 2x equals 1, divide by 2, and x equals 1 half. Well, we actually already knew that just from the math that we did up here. We already knew that 1 half was a 0. Now let's take the other piece and go x squared plus 9, set that equal to 0. X squared plus 9, set it equal to 0. And I can go minus 9 and minus 9. I get x squared is equal to negative 9. Square root and square root, and I get x is equal to positive and negative square root negative 9. Because when you square root one side, you get positive negative on the other side. And over here, finally, square root negative 9, and you get positive and negative 3i. So these are your solutions. What you see is that our solutions came in complex conjugate pairs. I have a positive 3i and a negative 3i, and I have my 3 zeros. My 3 zeros now are the 3i, 1 half, and negative 3i. Those are the numbers that if you plug them in, you should be able to get 0 when you plug those 3 numbers in. All right, it's tricky. Pause it. Try the one on page 8. See if you can do it. All right. First thing I'm going to do is verify. If you plug in, I'll save us some time. If you plug in 4i to each one of these, you do get 0. So we can say check. Yep, it works out. I know that 4i is going to be a 0 for that one. Now I want to find the remaining zeros. There should be a total of 3 numbers that I'm looking for. I know that because the degree says it. So I'm going to go on my calculator, and I'm going to go clear that out and go 3x power 3 plus x squared plus 48x plus 16, like that. Go ahead and hit graph. It's not the best graph, but at least we can see something. Okay, same thing as before. I know that this number right here, whatever that is, I found one of my zeros. So I know I'm looking for 3 numbers. So let's find it. So I'm going to go second, calculate, find the 0. Go here to the left, hit enter. Go to the right, hit enter. Right there. Oh, looks like negative 1/3. So I know now if I'm looking for zeros, I have 4i. I have negative 1/3, like that. And technically, guys, if you're on top of your game right now, you should know what the third 0 is. We have 2 of them, and if you know how the pattern works, you should be able to find all 3 of them right now. Let's say, hey, maybe you're not. Here's what we can do. We can take this, and we can use polynomial long division. I can say x minus a third, or I'm sorry, x minus a negative third. So if I wanted to turn this into a factor, it's going to be x plus 1/3. To clean it up, we're going to go times 3 and have 3x plus 1. All right, now I'm going to use this to break down this polynomial. Our good friend, the polynomial long division, is going to be 3x cubed plus x squared plus 48x plus 16, like so. 3x plus 1. Now, I already looked at my calculator to see that this right here is a 0. I know that my remainder is 0 if I do this correctly, because I know that this is a factor, which means it divides immediately. So 3x, I should get x squared right here. X squared times x should be 3x cubed plus x squared. That same weird thing where everything cancels out. So I'm going to drop down to 48x like so. 3 into this should be 16, so 16 goes over here. We're going to drop this 16 down, so we have 48x plus 16, and we got 0 for a remainder, like this. So if I wanted to factor it over the real numbers, my 2 factors would be 3x plus 1 and x squared plus 16, like that. If I wanted to find my zeros, I could set this equal to 0 and get negative 1/3. Let's get our zeros out of here. So I'm going to say x squared plus 16. I'm looking for zeros, so we're going to set u equal to 0. Go minus 16 and minus 16. X squared equals negative 16. Square root, and x is equal to positive and negative square root negative 16. So x is equal to positive and negative 4i. All right, I have all my solutions. I have 4i, I have negative 4i. Once again, these solutions came in complex conjugate pairs, just like I thought. So I've got it. If I wanted to factor it over the real numbers, it would would look like this right here. This is the best and simplest factoring. If I wanted to factor it over the complex number, so that means imaginaries are allowed, I'm going to say x minus this would be x plus 4i. X minus this would be x minus 4i. And x minus this, simplified, would be 3x plus 1. So this would be broken down into linear factors, everything power 1. But if you use this factoring, this would be using only real numbers, so we're all set. Hey, tricky stuff. I'll be here Monday, and we'll talk about it. Have a great day. Please.